Hello, I'm Arifur Rahman. I'm a data science at Cardiff Metropolitan University. My dissertation is comprehensive heart disease prediction using machine learning algorithms. In the next 10 minutes, I'll cover motivation, the data and pipeline, model results, explainability with shape, limitation, and future work. Now let's move into the introduction and context. Cardiovascular disease is a leading global cause of death. Additional risks scores and single model diagnostics often miss nonlinear interactions between risk factors. Machine learning can model those interactions, produce calibrated risk estimates, and support earlier, more personalized decisions. So, with this context, what's missing in the current studies? And what does this work add? Let's move into the research gap and contribution. Many papers compares a few algorithms or optimize in one depth. Fewer do side-by-side same data comparison across multiple models whilst also providing explainability and a basic fairness check. This project contributes a harmonized pipeline, a 6-model comparison, clear evaluation metrics, shape-based explanation, and pragmatic deployment nodes. So here is my aim and objectives. Aim are to design, validate, and explain ML models for heart disease prediction using a harmonized data set. The objective is a complete performance of 6 algorithms like decision tree, random forest, support vector gradient boosting, neural network, and K nearest neighbors. And then I will report accuracy, patient recalls F1, ROC AUC, and confusion metrics use shape to explain predictions, to run a basic subgroup and fairness check. So this is my objective. So I need to start collecting my data. My data name is UCBI Cleveland dataset that have 303 samples, and UCBI start log dataset that have 270 samples. Combined, it have 573 samples with 15 features. So there comes the data processing. So we need to handle with the missing values, the outliers, the future scalings, class imbalance, categorical encoding. So we used a stratified split to preserve class ratios. The datasets had higher diseases prevalences than the typically screening population. So we consider calibration and thresholding in interpretation. Now we want to jump in the methodology. So I am decided to divided my dataset into 2 parts, training and testing. So I put 75% in training and 25% in testing. And then we fixed random sets of reproducibility and quadrant against leakage. We report metrics at the same threshold and discuss trade-offs. Since clinical use may prefer higher recall even at some cost of operation, with this pipeline, so I use 6 machine learning algorithms, that is decision tree, random forest, support vector machine, gradual boosting, neural network, K nearest neighbors. So if I compare this model, decision tree for transparency, random forest for robust low variance performance, SVM for nonlinear separation, grade 1 boosting for strong tabular accuracy, neural network to compare complex interaction, and KNN as a distant based competitor. So now we will talk about the evaluation metrics. To evaluation my 6 machine learning algorithms, I will use accuracy, precision, recalls, F1, ROC AOC, confusion matrix. In a clinical context, missing a true case is costly, so recall often deserve extra weight. We put accuracy, precision, recall, sensibility, F1 balance of precision and recall, ROC AOC, threshold free ranking, and the confusion matrix to visualize error patterns. Model performance. So neural network and random forest are the top performer overall with strong accuracy and ROC AOC. Random forest typically leads on precision with when it flags disease. It's more often correct. Neural network typically leads on recall. It cases more to disease cases. SBM and grade 1 boosting are competitive and close behind. KNN tends to overpredict positive, yielding relatively higher recall but lower precision and accuracy. This trades off thresholds settings depending on clinical priorities. I add a picture from my programming to show the comparison of model performance. There is a correlation matrix. There is in-stock positive correlations with heart disease that THAL-K, OLPEC. Strongest negative correlation is THALEC, higher max heart rate, reduced risks. Notable relationship is negatively linked with THALEC. Feature importance. So when I want to work a dataset, I need to select some feature which is most important in this dataset. This is the THALEC. Most important, lower values increase risks. THAL, high cholesterol raises risks. OLPEC, higher ST depression signals greater risks. Age, risks increase with age. Therefore, high resting blood pressure is a strong factor. More blocked vessels increase risks. Certain blood discords linked to higher risks. This is the shape summary. So shape summary polls show direction and magnitude points to the right or red push towards disease, left or blue push towards no disease. We are strong positive contribution from OLPEC, Ka, and certain THAL categories. Higher THALEC tends to reduce predicted risks. On force or water views, we can explain a signal parent which features tended to the model and by now how much. A practical note, a dataset source indicate can appear seriously predictive. This is a BIOS leakage risk and should be removed or neutralized before deployment. This is the key result for my dissertation. This is the limitations. The external validity results are repositive. We need prospective validations. Some strong predictors come late in the pathway. Early screening may require alternative features. Remove datasets identifier some bias or leakage. Our dataset disease branches is higher than the general screening. Apply probability calibration before deployment. So for this datasets and this subject, I should some recommended future work like collect earlier stage features for screening, remove neutralized source indicates, run prospective clinical validation, deepen fairness analysis, and deploy a calibrated explainable prototype for fair pilot testing. In summary, neural networks and random forest based on this dataset and shape keeps decision explainable. With calibration and validation, these models can support earlier detection and more personalized care. Thank you for watching. This is the reference. Thank you.